to disappoint. Yeah, let's get started. So my thesis is titled on margin-based generalization prediction in deep neural networks. Now, since this is a public lecture, my target audience really is the public. So I'm going to try and keep everything as simple as possible. I'm going to completely disregard some extra details and things. So hopefully for the technical members of the audience, doesn't feel like I'm giving you a verbal lobotomy or something. So I hope that you will find it interesting regardless. And I'm sure there will be some things that is of quite some interest to you. Okay, so just a quick overview. The talk is kind of split into two informal parts. The first part is going to be a bit of background on deep neural networks. So I was thinking, since it's a public lecture, even if you come away from this not really understanding my research, if I could just teach you a bit about how deep neural networks work, I see that as a win. So yeah, we'll go over that background. And then the second part will be really focused on the research I did in my PhD. So about 30 minutes for each part. Okay. So the title, on margin-based generalization prediction in deep neural networks. You're probably wondering, okay, what's a margin? What's a deep neural network? What's generalization? So I thought, let's look at each three of these terms individually, give you some background. And then from there, you should have a much better understanding of kind of the problem that I was tackling in my PhD. Okay, so let's start with deep neural network. Okay, so a deep neural network, you've probably all heard of it. It's revolutionized the field of artificial intelligence. With deep neural networks, we can do amazing things. We can generate images, for example. This is probably one of the coolest examples. So for example, here, the user can enter a text prompt, something like a raccoon astronaut with the cosmos reflecting on the glass of his helmet, dreaming of the stars. And the neural network generates an image that looks like that for you. Or in this one here at the bottom, this is the famous painting Girl with a Pearl Earring by Johannes Vermeer. Now, what we did here is something called outpainting, where we asked the neural network to fill in the background around the painting. So the original painting was kind of just this little square here, and the neural network filled in all the rest. So this is really amazing. And of course, there are things like language models. You've all probably heard of ChatGPT, which is mostly used by students to cheat on assignments. That's really something that is quite revolutionary, that we can really talk with these agents and they can be useful to us. So in this case, it wasn't that useful. I asked it to help me with a few problems with SARS, and it declined to give me any information. Okay, so deep neural networks, besides just doing cool things like this, they've revolutionized many things. Things like healthcare, understanding human language, recognizing images, classifying objects. In any modern AI system, you're going to find a neural network in there somewhere. So they're very important tools. Now, what is a deep neural network? So I'm using a very non-technical definition here. I'm just going to call it a big function learned from data. But let's look at these words a bit more carefully. So let's start with a function. So a function really just describes the relationship between two things. You give it some input, so something goes into the function does something with that, and then you get something else out. So really, you're just describing some relationship between an input and an output. So of course, in neural networks, the functions we're describing are quite complicated. It might be something like the input is an image of a frog. The neural network here is your function, and it tells you that that is a frog. The network can literally understand what it's seeing in an image. Although the word understand is a bit loaded, it can classify what it's seeing. Or similarly, your input might be, hey, ChatGPT, write a poem about frogs. And the neural network outputs you a poem on frogs. Amidst the reeds, a gentle croak, moonlit ripples where green dreams soak, frogs sing secrets of the night, which is, I think, actually pretty good. Okay, but unfortunately, while I've represented neural networks as this cute-looking robot, um, the actual reality is a bit more nefarious. This is what a very simple neural network looks like. So a neural network really consists of things that we call neurons. So these blue little dots here, these are called neurons, and these black lines that connect them to each other, we call weights, or alternatively, we also call them parameters. So a neuron is really actually a very simple function in itself. So a neural network is kind of just this combination of small, very simple functions. So all a neural network does is it takes some input, it weights each input, and it sums it together. So here's just a very simple example. Here we have our weights. I've just assigned kind of random values to them. And here we have our inputs. So all the network will do is say the output is 1 times 2 plus 3 times 1 plus 5 times 1 plus 2 times 3. And then you get the output of 16. So yeah, that's really basically all that a neuron does. So in the neural network, these neurons are connected to each other. So you'll see here, for example, if we look at this one here, it's connected to all of the previous nodes here. These lines represent different weights. And similarly, in the next layer, this neuron is connected to all the neurons in the previous layer. So if we look at the example of, say, this neuron here, or I should mention, so this input, this isn't actually a neuron. This just represents our input data. So our input data is usually like essentially a sequence of numbers. So things like text that the user inputs or images, we can all just usually represent that as numbers. So we take an image, we turn it into numbers, and now it looks something like this. So this is our input to the neural network. And then these layers, these are what we call the hidden layers. So that consists of actual neurons. That does the processing in the neural network. So if we look at, say, the neuron here, if we give it this input, each input has a corresponding weight for this neuron. So then we just do the whole multiply and sum together thing again, and then we get an output of 2.961. Then we can do the same for all of the other neurons in the network. So each of them has their own sets of weights connected to all of the inputs. Okay, now if we want to move on to the next layer, the next layer's nodes, it's taking this layer's nodes as its input node. So then we just repeat this process. So now we get a new set of values for these nodes. Then we just do that again. And then finally, we get our output. So this is just the output of the neural network, which is, again, a string of numbers. We can then convert that to, say, text, to a poem about frogs. At the end of the day, it's really just numbers being processed by these sequential layers. That's really, in a simplified manner, all that a deep neural network is doing. Now, why am I telling you this? Well, it turns out that this kind of mathematical structure of a neural network, this combination of nodes that weigh things and sum them together, is very useful. It's what we call a universal function approximator. And all that that really means is that it's mathematically proven that this structure of a neural network, this mathematical idea, can represent almost any function we want. So for one set of weights, a neural network can represent a function that looks like this. And for a different set of weights, a neural network can represent a function that looks like this. Or more usefully, if you make the network big enough, for one set of weights, it can actually understand human language, or it can actually understand what different images and objects look like. So you can see why this is very useful. We've got this kind of structure of nodes, and they're organized into these layers. And depending on how we pick the weights, we can essentially make the neural network do almost anything. But as I said earlier, a neural network is a big function learned from data. So the question becomes, okay, how do we pick these weights? So say you're trying to do something, say write poems about frogs. How do we choose the correct weights such that the neural network can actually understand natural language? And that is where data comes in. So I'm going to use a very simple simple case of we're trying to distinguish between cats and dogs. We're trying to build a neural network. You give it either an image of a cat or a dog, and it tells you which it is. So if a picture of a cat comes in, we just want the network to say it's a cat. If a picture of a dog comes in, we just want the network to say it's a dog. So to do this, we need data, and specifically, we need labeled data. So by that, I mean is just that for every picture of a cat, we also have a corresponding label that it's a cat. So this might have been created by humans. A human could have looked at a lot of cat dog pictures. Every time he sees a cat, he just marks that as a cat. Every time he sees its dog, he just marks that as a dog. What we end up with is the data set where for every image, we know whether it's a cat or a dog. Okay. What we do then is we take our images and we just set the labels aside for them. Just put them there in the corner. Now we give these images to our neural network. It goes through the network, and the network is going to produce some predictions. So it's going to produce a string of numbers, and then we can kind of convert that back to either being a cat or dog. So our predictions might look something like this: dog, cat, something, something, cat. And our labels is cat, cat, something, something, dog. Now what we do is we define what we call a loss function. So loss function really is just a measure of how wrong was the neural network. You can think of it as kind of saying the labels minus your predictions. Gives you an idea of, for this set of images, how inaccurate was the neural network. So a high loss would mean that the network is very wrong. A low loss would mean that the network is very accurate. It's correct most of the time. Now, the interesting thing about these loss functions is that we can actually use this information of how wrong the network is to improve it. So what we do is we use a bit of mathematical wizardry, really. It's an algorithm called gradient descent, an optimization algorithm. I'm not going to go into it. But essentially what it does is it just asks, how can I update each weight such that the loss goes down? So just how can I nudge the weights such that the network makes less wrong predictions? And then using that information, we can update our weights, and now the network should be a bit better. Now we just repeat this process. We pass images through the network, it makes predictions, we compare it to the labels with our loss function, and we update our weights, and we do this for, say, thousands, if not millions of images. And eventually we find that our network can really accurately distinguish between cats and dogs. So we can actually visualize this in a simple case. So I've got a very short YouTube clip I want to show you, if that explanation wasn't clear. Just make this full screen. Okay, so I'm just going to pause here. So what you're seeing here is these red dots. These are our data samples. So when previously we had pictures of cats and dogs, now we just kind of have these dots. And what we want our network to do is to learn this kind of function. This blue line here represents the function that the network has learned up to this point. So you'll see when it starts learning, the loss there in the top left corner is pretty high. And you can see that this blue curve is really not fitting the red curve. But as it learns, you can kind of see how the network starts learning how to approximate this function. So it's trying to fit the data, and we see that the loss starts going down. And eventually, we see that the neural network does a pretty good job, and it seems to have been able to fit that data. Okay, so that's really neural networks in a nutshell. Okay. So this is very strange. This is completely counter to kind of traditional software programming. We're not telling the network, if you want to distinguish between cats and dogs, go and look at the shape of the ear, or look at the noses, or look at the size of the animal. We're not giving it any such information. All that it knows is it's seeing an image and it wants to update its weights to reduce the loss. That's all it's trying to do. This means that the network is learning by itself what to look for in the image. It's learning the kind of things, maybe it's the shape of the ears or size of the tail or the fluffiness of the animal or something. It's learning by itself. We're not giving it that input. So a lot of people have actually gone as far as to call this a form of alien intelligence. It's literally not something that us as the programmers are encoding into it. It's learning these decision-making rules kind of simply from the data. Now, this can have some unintended side effects. So there's a very famous story where a bunch of students were trying to make an image classifier that was supposed to distinguish between huskies and wolves. And they trained this classifier, and it seemed to be pretty accurate. But then they realized that, most of the pictures we had of wolves was in snow. Well, the pictures of huskies was kind of in other terrain, on grass or somewhere in the dirt and such. They realized that the network had actually learned nothing about what a wolf is. They had built a snow classifier. If it saw that was determined to be a wolf. So yeah, the neural network can literally cheat if your data essentially is cheatable. So it's for this reason that neural networks really are quite strange. Okay, yeah, so that's neural networks in a nutshell. I'm now going to move on to the second term, generalization prediction. Okay, so following up on our previous example, we showed it a bunch of images of cats and dogs, and we showed it to him many times, and this neural network eventually graduates. It's a very good neural network, and we see that it gets 100% classification accuracy. So that just means for every cat or dog that comes in, it always picks the right category. It's always able to say this cat is a cat and this dog is a dog. So it's a very smart neural network, clearly. However, we don't just want our network to work on the images it has seen. So say a dog was sitting over here, and I took a picture with my camera and sent it to the neural network. That picture isn't going to look exactly like one in the training data. The angle might be different. The lighting conditions might be different. The background will be different. We really want our neural networks not only to work for the data we train them with, but to work in the general case, to work outside there in the world. If we put up a neural network somewhere in a dog park with a camera, we want it to be able to tell us if a dog or a cat walks by, for example. So what we mean by this is that it has to generalize beyond its training data. It has to learn something general, something that's applicable to the world, not just to the data that it was learned on. So what we usually do is we keep some data separate. This we call a test set. This test set we never teach the neural network on. We never change its parameters or its weights after looking at these images. It hasn't seen these images before. So once we're done training, we then show the network these examples of cats and dogs that it hasn't seen before. And maybe in some cases you figure out, your neural network really isn't quite bright, and it only gets, say, 55% classification accuracy, which is a very poor performing neural network. So this brings me to this meme that I found on Twitter. This guy, it's formerly Twitter. Evaluating a model on training data is like asking your mom if you look good. So you're not going to get an answer that really reflects reality. I'm sure my mom would disagree. Yeah. So the term generalization really just means performance on unseen data. If we say that a neural network generalizes, we mean that it's performing well on data that it hasn't seen before. Now, generalization in deep neural networks isn't very well understood. We're not quite sure why some networks have kind of PhD level intelligence and why some, wear the dunce cap. So this is a completely open research question. Because they learn in this strange manner where they just pick up patterns and things from their training data, it's very difficult for us to understand what they actually learned and how they learned it, and did they learn it in a good and proper manner that will generalize to the real world. So this is really what the theory research at Must Deep Learning is concerned with, is kind of getting to the bottom of why neural networks generalize. Now, why do we care about this specific research question, understanding why neural networks generalize and when they don't? Well, there's a few reasons. Firstly, so there are many, we call this hyperparameters for modern neural networks. So during that learning process that I showed you, you as the practitioner, the guy actually training the neural network, there are many knobs and dials that you kind of have to set and play with to get the neural network to actually properly learn something. And this can be a very time-consuming process. Usually we do it kind of by a process of elimination. Let's try all of these settings and just see which one performs best. And the reason we do that is because we don't yet really understand what kind of choices lead to networks that generalize well and which kind of choices don't. Another reason is improved performance. If we can actually understand what is the qualities of a neural network that generalizes well, we should be able to use that information to actually make them work even better. Thirdly, better interpretation. So as I mentioned earlier, it's usually quite difficult to interpret a neural network, to realize for this prediction it's making, why did it make this prediction? And this is a very important problem. If we understand kind of the building blocks of the neural networks better and how they work in essence, that should lead to us being able to offer better interpretations of the neural network's decisions. And fourthly, simply for the love of the game. This is an interesting research problem, and it's a difficult one. So yeah, it's really something fun to work on. Okay, so now let's get to the prediction and generalization prediction. So one way to investigate generalization in deep neural networks is to try and predict for a given network whether it's going to perform well or whether it's going to perform poor. So the question really is, can we design some measure to predict how the model will do? So is there something we can measure the neural network, something about its weights, something about the representations it learns, or really anything that will tell us if this neural network is going to perform well in the real world or if it's not going to perform well? And this generalization prediction, this idea of predicting if the network is going to do well or not, that really was the main focus of my PhD. Now, there is actually a benchmark to investigate generalization prediction. So this thing is called the PGDL challenge. PGDL just stands for Predicting Generalization in Deep Learning. And it's a challenge that was held at a very big artificial intelligence conference in 2020. And what it really consisted of was just a bunch of models. So let me be more specific. So firstly, you'll see that in this table, there are a bunch of tasks. So each task really just refers to a group of models. So if we take the example of task 1, this is 96 different deep neural networks. And they're all trained on the same data set. This CFAR10 is just a very common image classification data set. You have to distinguish between cats, dogs, planes, cars, trains, things like that. Now, these 96 models, they all essentially get 100% accuracy on their training data. So all of the networks performed equally well on the data that they had seen. They're very accurate. However, on unseen data, on the test set, there is a large variation. The poorest performing network only gets 66.83% accuracy, while the best one gets 86.34%. This is a big gap. It means the one network makes a lot more mistakes than the other one. Now, the other tasks are similar. So for example, task 2, it's 54 models. They also all have perfect train accuracy. They're just trained on a different data set. So this is SVHN, which is also just another publicly available image classification data set. Okay, now the goal of this challenge is generalization prediction. So in essence, what we have for each task is we've got a training set of models. So we've got 4 models that perform excellent on their training data. They all perform the same. But if you evaluate these models on the test data, then we see that some of them are very bright and some of them are less bright. So what we want to do is we want to define some measure of the neural networks using only their training data and the network itself. We want to see if we can predict which model will perform better than the other one. So we're really, in this kind of silly analogy, we're trying to assign the correct hats to the different neural networks. So we want to be able to say, this is the best network, this is the second best, this is the third best, and this is the worst or the fourth best neural network. And then at the end of the day, we just compare how well our measure did with their actual performance on unseen data. So in essence, we're just trying to predict how well each model will do. It's really the simplified idea of this challenge. At the end of the day, we want something that looks like this. So each red dot on this graph represents one of our neural networks, and each neural network has a corresponding test accuracy. That's here on this y-axis. On the x-axis, we have our measure, something that we measured about the neural network. So we want kind of a strong relationship between our measure and the test accuracy of the neural network. So in essence, if we were to rank the models according to test accuracy, we'd say this one is the best, this one is the second best, this one is the third best, etc. And we do the same with our measure. So now looking this way, and then our measure would say this one is the best, this one is the second best, this one is the third best. So yeah, we really just want the ranking of our measure and the ranking of the true ranking of the models on the test set to align well. That is kind of the goal. Okay, now we're going to look at one way of doing generalization prediction, margins. And margins excite me immensely. So to explain margins, I'm just going to start with a very simple two-dimensional data set. So let's say I was walking around there in Armanus and I was observing a bunch of cats and dogs. And I decided to measure their heads and to also record on average how many hours do they sleep a day. So each of these blue dots would correspond to the measurements taken for a cat, and each of these red dots would correspond to the measurement taken of a dog. So you can see that the cats, they tend to be at the top left here because they sleep for more hours a day on average, and their heads are generally smaller. Similarly, dog heads are usually a bit bigger, and they tend to sleep for less hours a day. Okay, so now we've got this two-dimensional data set. Now, if we were to let a neural network loose on this data set, such that it learns how to distinguish between cats and dogs, what you can think of it as doing, what it's actually learning, is a decision boundary. So a decision boundary is kind of just how the neural network learns to distinguish between cats and dogs, how it learns to distinguish between the two classes it's investigating. So this decision boundary is essentially just saying that the network will classify everything to the left of this gray line as a cat and everything to the right of this gray line as a dog. Here in the middle, the network isn't sure. It would probably say that that is a cat dog. It's equally sure it's a cat and also equally sure it's a dog. So it's really just completely unsure. So can we visualize these decision boundaries of neural networks? So can we kind of look, I just said that neural networks are very mysterious. We're not quite sure what's going on, how they're learning. Can we just visualize these decision boundaries, and that would give us some information of what they're doing, the things they're learning? Unfortunately, we can't, due to the curse of dimensionality. So, so the curse of dimensionality, let me just explain that. So in this example that I just went over, we have two dimensions. We have two features. We have the size of the animal's head, and we have the hours slept a day. But say now we recorded another feature about the animals, maybe the size of the tail. We can represent that data set then as this three-dimensional plot. So this isn't actually this data set, it's kind of just one I borrowed from a paper. But you can see now we've got this third axis. We're not only going left, right, up and down, we've got this depth as well. We can go forwards and backwards. So this is an example of a three-dimensional data set. But now for 4 dimensions, say we add a fourth feature. Maybe it was, I don't know, the cuteness of the paws was the fourth feature. How do we visualize this? Well, for us humans, it appears we can't really. We live in a three-dimensional world. You can go left to right, forwards, backwards, up and down. Fourth dimension, there's really just kind of no way to visualize 4-dimensional data, how they relate to each other. So this fact that we really can't visualize this is a big issue. Now, for example, in the PGDL challenge, when we're working with image classification, so images really just consist of a bunch of pixels. So each pixel is kind of a numerical value, and each of these pixel values for this 3 here, this is just a 3 from a well-known data set called MNIST. Each of these pixel values serve as input to our neural network. So each of these pixels is an input feature. Now, there are 28 pixels in a row and 28 pixels in a column. 28 times 28, that means an image is 784 dimensions. That is so far beyond what humans can grasp. It's simply, you know, if we stop at 3 and then kind of our intuitions break down. So there's kind of no way we can visualize decision boundaries of a neural network if it was trained on image data. In fact, it gets worse. Say we have this cat. This seems to be a very sleepy cat. This is from the CFAR10 data set. Now we have color. So now we have 3 numerical values for each pixel in the image. So that means, and in this case, the image is a size 32 by 32, but we have 3 color channels. So it turns out this cat is 3072 dimensional, which isn't ideal. So this is where margins come in. So a margin really is just the shortest distance to the decision boundary from some data point. So just to give an example, if we were to look at this dog here, the margin is the distance indicated by this purple arrow. What we're really asking is for this sample in our data set, this little red dot of a dog, how much bigger does its head, or sorry, smaller does its head have to be, and how many more hours a day does it have to sleep before the neural network will think it's a cat? So a margin really is just the distance of how far you have to move this data point of ours before the network is going to classify it as something else. So that's really all that the margin is. So maybe just to give an image example, what we have here is we have a turtle and we have a cat in a box. And here we've actually computed the point on the decision boundary for an image classifier network that performs really quite well. So we'll see as we move to the right here, this turtle starts to turn into a bird. So that's we're basically moving the turtle from the turtle class that the network thinks it is, and then moving it across the decision boundary until the neural network thinks it's a bird. And this is kind of how you can visualize that. Here in the middle, the network is going to be unsure. It's going to say that it's both a turtle and a bird. So this would be a point on the decision boundary, and this would just be a point in the bird class. Similarly here, we've got a cat that's been moved to the class dog, and you can see that it gets much more dog-like as we go along. Once again, here in the middle, the network is going to be unsure. It's going to say there's equal probability of it being a cat and equal probability of it being a dog. So you can already see why margins can be useful for generalization prediction. If you're saying that for my network, say we're working with our cats and dogs classifier again, it sees an image of a cat, The margin really is an indication of how much do we have to change this picture before the network thinks that it's a dog. So you can imagine that if you don't have to change it much and the network immediately changes its classification, that's probably not a very good network. So what I'm visualizing here is just a simple data set. You've got two classes, and this is the decision boundary in the middle. And we can see that we have large margins. You have to move each training sample quite a bit before its classification changes. In this case, we have a non-optimal decision boundary, and our margins here are now very small. You can just slightly move this one or that one, and the neural network is going to classify it as something else. So generally, we think that large margins are better, and that a network that has larger margins should mean that it generalizes better, that it does better on data that it hasn't seen before. Yeah, so really, we're looking for decision boundaries that kind of optimally separate our 2 or 10 or 100 classes. Doesn't matter how many you have. We just want the neural network to optimally separate our training data. So as I mentioned, we can do these sorts of visualizations in neural networks, especially on image data. But this is why I love margins so much. This is why I'm kind of obsessed with them, because they're like little torches in the dark. We've got a picture of a cat, and we have no idea what this 3,000 dimensional region around the cat looks like from the neural network's perspective. We have no idea. But what we can measure is just how much do we have to change the cat before its classification changes, before the neural network thinks it's a dog. So it gives us this little glimpse into what's going on in that 372-dimensional space. So really, margins are kind of like whispering little secrets about the model to us. And we can use this information to try and understand that better. If it sounds like I have a borderline autistic obsession, I really just bear with me. Margins are this relevant. Okay, so that really concludes the kind of the background section of the talk. So now you've got hopefully a good idea of the inner workings of deep neural networks. You understand what I mean by generalization prediction. We're trying to tell if a model is going to perform well on data it hasn't seen, or if it's going to perform poorly. And you have a general idea of what a margin is. So now I'm going to move into the actual research I did during my PhD. And I'm going to start with some limitations of prior methods. So this was kind of the first part of my thesis, is kind of looking what other people have done in terms of margins for generalization prediction, and what we can learn from this prior work. So up to this point, the examples I've been giving you of margins have all been in the input space. We're looking at our input data and looking how far we can change this image of a cat before it becomes a dog or whatever. However, the most popular method at the time for generalization prediction was to actually measure the margin here at the hidden layers. So this might sound wildly confusing. Let me just give you an example. So what you can think of each hidden layer in a neural network doing is that it's actually transforming your input data in some way. So if this was our input data, our little dogs and cats example, after this goes through, say, the first hidden layer in the neural network, what that hidden layer has done is it's essentially transformed that data. So now the data might look something like this. What the network in this case has done is it's learned that, oh, if I pull these two classes apart, then it's easier to separate them. So that's really the kind of the intuition of what I call hidden margins, measuring margins at the hidden representations. And at the time, this was a very popular method for generalization prediction, and there's a bunch of work that has been done surrounding this. However, we evaluated this method and we started looking for problems. So the biggest problem with this kind of method is simply that the different neural networks you're comparing, they don't always look the same. So in this case, we have a rather small neural network. It only has one hidden layer. In this case, we have a bigger neural network, and it has 3 hidden layers. So this causes some issues. Say you're measuring the margins over here for this network at its first hidden layer. Now you have to compare that to some margins measured for this neural network But now, which hidden layer do you choose? There are three of them. Do you say, okay, but let's just take the first one? Do we take the middle one? Do we take the last one? Do we take all of them? And we actually found that depending on which layer selection you kind of choose, do I always use the first one? Do I always use the last one? The generalization prediction results of hidden margins can vary greatly. Sometimes you get good performance, but sometimes you can also get very poor performance. And of course, there's no way to know beforehand which kind of selection of the hidden layers will work best. Similarly, sometimes the layers have different sizes. So in this example, we have 10 nodes in this hidden layer, but this hidden layer has 20 nodes. So now this causes an issue when we're measuring margins. So remember that margins really are just distances. So now we're measuring a margin here, which is in this 10-dimensional space. And now we're comparing it to a margin measured here, which is in this 20-dimensional space. And just by the way that distances work, it's very difficult to compare distances that are measured in different dimensionalities. This is really a difficult problem. It's like saying that kind of, if you're just on a rugby field, how far the other player is away from you, that's like essentially a two-dimensional problem. But now say that people had magic brooms and they could fly around. Now you have to kind of take this extra upwards axis into account as well. So is the person hovering over there further away from you really, or just the person here on the ground? It's difficult to compare these distances. And then finally, these layers can also be on different scales. So the one neural network, maybe it's neurons here, the values they output is maybe kind of in the range of 0 to 1. For one sample, it might output a value of 0.5. For the next sample, a value of 0.6. But the other network here, its range of values are a lot higher. It might be in the range of 10 to 100. So for one sample, it outputs something like 16. For another sample, it outputs something like 80. Now, the problem with these differences in scale is you're trying to, I don't know, compare kilometers with millimeters. The one network is working on millimeters, the other one's working with kilometers. How can you accurately compare the margins of these two networks? So yeah, we experimented with this quite a lot, and we identified these three issues, and we were actually able to show empirically that it is an issue. So what I'm showing here on the left, each of these red dots again represents a model. And then on the x-axis here is its mean hidden margin of that model. So all we did is we took a bunch of random training samples, and then we measured the margin for each of those samples at one of the hidden layers. And then we just took the average of that. So you get a single value. So for example, for this network, say here, we can see that it had a mean hidden margin of 0.035. On the left axis, it's just the test accuracy of the model. So that's how well it actually performs on unseen data, how well it generalizes. You can see that here our measure does a pretty good job of predicting generalization. There's a very good correlation between our measurement, mean hidden margin, and the test accuracy of the model. And we can actually quantify this using something called Kendall's rank correlation. So I'm not going to go into how Kendall's rank correlation works, but it's essentially, you can think of it as a score where higher is better. A score of 1 would mean that you are predicting generalization perfectly. A score of 0 would mean that your measure is saying absolutely nothing about the generalization of the model. So ranking correlation of 0.71 is, it's a pretty good correlation. However, if we then apply hidden margins to a different task in the PGDL dataset, we see a very low correlation. It's very near to 0. And you can see that there really doesn't seem to be any useful relationship between mean hidden margin and test accuracy. So what's happened here is that one of those three issues I listed, it didn't seem to be a problem for these tasks, for these models, but it clearly was a problem for the models in this task. The point I'm trying to make is that current hidden margin-based measures are unreliable at predicting generalization. Okay, so let's move on to my solution. So I've just told you about the sins of hidden margins. Basically, we have these issues, the number of layers, the size of the layers, and the scale of the layers. So we started thinking, okay, but how about the input space? Why don't people use the input space? The input space doesn't have any of these issues. So the input space, again, would just be measuring the margins here, like just to the decision boundary that your network has learned in the input space. So we don't have to worry about different number of layers because we don't have to choose different layers between different networks. We always just use the input layer. There's one. It's not difficult to choose if you only have one option. The size of the layer is of the same size. It's the dimensionality of the input data. So in this case, this layer size will always be 2. It's the same scale. It's the same data. So it's not like the one network is measuring the size of the head now in kilometers and the other one in millimeters. It's standardized. And since all of the networks are trained on the same data, just measuring the margin in this input space should solve all of these problems. So very anxious for these results. Turns out it doesn't work. Yeah. So we see here again a very poor Kendall's rank correlation. It's very close to 0. We can see between mean input margin of these models and test accuracy, there is very little relationship. Mean input margin is not accurately predicting test accuracy. In fact, what's quite funny about this graph is if you were to say, I want to choose the model that performs the best on unseen data, and you use this measure, it would identify this one. This one has the highest input margin. But it's actually the model that performs the worst of all of them. So it's really not a good measure. Okay. So the question became why? Why is this happening? Why do input margins not predict generalization? With hidden margins, we came up with all these limitations, and that kind of makes sense. But with input margins, we couldn't really think of much as to why it's not working. So we kind of started thinking, when we're thinking about margins, even though it's so high dimensional, you kind of have a mental model in your head. So when I was thinking about margins, I always imagined something that looks like this. Got 2 classes separated, bigger margin means it's better, etc. I said, how about we slightly shift our mental model? What are the things that could go wrong if it doesn't look like this? So I hypothesized that maybe what's going on is that the decision boundaries kind of look more like this, kind of curved around the data. So in this case, we've got 2 features, x1 and x2. And you'll see that between the data points, this value of x2 doesn't vary a lot. So in this analogy, this would be, say, the size of the head. This is our feature, the size of the head. But there's very little variation between the data points in terms of the size of the head. Although in terms of feature x1 here, this might be the hours slept a day or anything really, there's a lot of variation. You can see that there's a wide range of values for our training data. So if we're going to measure a margin, recall that the margin is the shortest distance to the decision boundary. So for this blue sample here, we'd be measuring the distance to the decision boundary here. This would give us the margin, the shortest distance to the decision boundary. But now you can imagine that kind of measuring it there, that doesn't tell you really anything about how well these 2 classes are being separated. It's kind of a useless measure. However, what we actually want to do is we want to measure the margin kind of in this direction, so kind of towards the other class. So using this information, we designed a method that we call constrained margin. Now, what constrained margin does is it essentially just asks, okay, what do I think is the important directions that we should be measuring in? So we don't want to measure in these kind of directions. We want to measure in these kind of directions. So in this little mental model, the important direction is the one where there's a lot of variance in the data. And we can actually use a well-known mathematical tool for this called principal component analysis. So all that the principal components do really is you give it your training data and it identifies the direction of highest variance. So what I've shown here is the direction of highest variance in this training data given by this green line. So that's called principal component 1. And then the direction in the input data that gives us the second highest variance is this purple line, and that's called principal component 2. So yeah, we can determine in our training data which directions give us the highest variance across our data. So we then designed this constraint margin method. So I'm not going to go into the math. This is kind of what it looked like, how our final technique looked like. I'm just going to focus on this little picture here, which is basically just an easier description of this. But if someone is really interested in this, then please ask or come talk to me afterwards. So what we did is we said, okay, instead of just trying to find the shortest distance to a decision boundary, let's try and find the shortest distance to a decision boundary in some specific direction. So this is called a principal component subspace. You don't really have to worry about that terminology, but I think this little graph illustrates it well. We've got some three-dimensional input space just for illustrative purposes. What we do is we find the top two principal components of the data set. So the two directions that explain the most variance in the data. And then we just say, okay, when we're trying to find a point on the decision boundary, so we can measure the margin, measure the distance, we're just going to constrain that search to this plane. So this plane, really, you can think of it as a principal component subspace. We're saying that we've got this 3072 dimensional space, but we're going to only look for a point on the decision boundary in, say, a very specific 10-dimensional space, or even a 2-dimensional space. And then we're going to measure the margin in those directions. So just to kind of make this easier, if that's not clear, we're basically saying that for each sample, we're only going to look in this direction given by this green arrow. So for this sample, we're going to look in that direction. For this sample, in that direction. This sample, in that direction. We're going to ignore everything else that goes on in that other direction. And that's how we're going to measure our constraint margin. Okay, so we implemented this and we tested on the PGDL benchmark. And our results looked very good. So what I'm showing here are those correlations that I showed earlier. So remember, 1 would be perfect. We want to be as close to 1 as possible. These are just the different tasks and the data sets that we're trying on. You can just ignore that. But what I want you to look at is these 4 columns here. So for each of these tasks, I'm showing the correlation that my method got at predicting generalization. And at the bottom here, I'm showing the average. And you can see that our method, constraint margins, compared to normal input margins, has a much higher correlation on average by quite a large margin. Compared to hidden margins, it also performs very well. It performs better than different hidden layer selections as well. So really, this is essentially the best margin method for generalization prediction at the moment. In fact, I went as far as to compare it to all of the other solutions that have been offered for this PGDL benchmark. So these are kind of the authors and their scores, their average scores throughout the year. So the score isn't correlation, but once again, higher is better. Just think bigger number means better. And you can see how these scores have gone up over the years. And the previous person with the higher score was Schiff et al. In 2021. And yeah, we beat him again by quite a bit. So this method of constraint margin is at the moment the state of the art for generalization prediction in deep neural networks. We have the best scores in the world, essentially. In fact, it worked so well that we wrote a paper about this called Input Margins Can Predict Generalization Too, which I presented in Vancouver earlier this year. So if anyone ever tells you that margin is a useless measure, tell them no, it can get you a free holiday to Canada. Right, okay, on to the final part. So this is going to be very short. I'm close to wrapping up. So every PhD thesis really has to have a core idea, a core thesis. And mine, I can really just sum up as directions matter. in the neural network's input space, or the input space that it learns, some directions are really a lot more important than others. You want your decision boundaries to be far away from your samples in the important directions, and in the other directions, they don't necessarily have to be far away. And if you want to do generalization prediction, you really have to take the direction into account, the direction in which you're measuring into account. Yeah, and that's basically the core thesis in a nutshell. In fact, we did a little experiment. So what we did here is we just said, okay, let's choose the directions we think are the best for a specific task. So this is task 1. And then we calculate that for all the networks, and we measure that correlation. And then we choose directions that we think are not as good, and then even worse and even worse. And you can see that as you choose different directions, these correlations drop significantly. We go from being very positively correlated to actually being quite significantly negatively correlated generalization. So just what this shows is that if you choose different directions, it doesn't predict generalization well anymore. And we see similar results for task 4 here. So yeah, this very much supports my notion of directions matter. Okay, so I don't have time to get into the other interesting things. This was kind of the main idea, the main part of my PhD, but we did a bunch of other things. So there are many ways to measure a margin. Margins are actually quite difficult to measure. So there's a bunch of techniques. We experimented with if you're doing generalization prediction, does one way of measuring them work better than another one? And we actually found that it generally doesn't matter that much. We investigated margins and noise. This is a paper I wrote with my co-supervisor, Dr. Tian. So what we did is we introduced some artificial noise into a data set, had the network learn that, and see what effect it had on the margins. And also we looked at margins and adversarial robustness, but that's a conversation for a different lecture. Okay, so thank you very much. I want to also especially thank my advisor, Prof. Marley, and also my co-advisor, Dr. Tian, the whole Must Deep Learning research group. It's really been a great environment, and loved working with all of you. And of course, SANSA, who sponsored or funded a large part of the PhD. So yeah, questions?